We'll talk about Dirac equation in 2+1 dimensions.
Okay, so I discussed Dirac equation in 3+1 dimensions. Now I will discuss it in 1+2 dimension. But to make it relevant to graphene, so let me remind you what Kashyap has told you. So in graphene, as you have here, he has told you, we have a hexagonal layer with unit cell containing two atoms A and B. And belonging to two sublattices. So let me also remind you the lattice vectors which he introduced. And where A is 1.42 angstrom is the carbon-carbon distance. And he also introduced Dirac points K and 2 pi 3a, 1, 3 under root, and 2 Dirac points 2 pi 3a, 1 minus 3 under root. Okay, so let me go through a little bit derivation of this Dirac equation which he wrote down. So since I am more familiar with Sankar quantization, so let me write the Hamiltonian in the tight binding approach which he described. So the Hamiltonian is minus T sigma I j I dagger bj plus hc, where this A and A dagger as usual are annihilation and creation operators corresponding to the sublattice A and to the corresponding sublattice B. Okay, so these are annihilation and creation operators.
Are the fermionic that satisfy A dagger satisfy anti-commutators?
Yes. So these are annihilation and for an electron actually, for bound electron in this tight bonding in the sublattice A with an equivalent definition for the sublattice B. Okay, and T, as he explained, is the hopping energy, the hopping between different sublattices, as he explained, and T is 2.8 electron volts. Now, as we do in field theory, we take the Fourier transform of these, so we can have a Fourier decomposition of A, K, J, e raised to power I, K dot Uj. So instead of K dot R, we write it as Uj, and similarly for B. And then we can take these Uj as lattice vectors. Instead of XR, we take them as the lattice vectors A1 and A2. Okay, then you can easily see the H will be sigma j, A, K, J dagger, B, K, J dagger, time the Dirac Hamiltonian, which I will write A KI KJ B KJ, where this HD is equal to HAB star 0 and HAB is equal to minus T e raised to power I K dot A1 plus e raised to power I A K dot A2. Okay, so we have this one here where HAB is. So let me write K as near, so I will expand near the Dirac point K prime plus P. So if I expand it around this Dirac point, then HD will be equal to minus T 0 minus I over 2 P dot A1 plus A2 and minus I by 2 P dot A1 plus A2 minus 3 under root over 2 P dot A1 minus A2. These factors come because of these coordinates here of K prime. Okay, and this will be just I by 2 P dot A1 plus A2 minus 3 under root over 2 P dot A1 minus A2 and where A1 plus A2 as component 3 1 0 and A1 minus A2 as 3 under root 0 1. Okay, so then if you do that and put just this value, the HD here will be 0 I Px plus Py and minus I Px Py 0, and which you can write in the form, if you use Pauli spin matrices, you can write it as equal to okay, so there is this factor T also coming in, so we will have this equal to, actually this Vf comes here, where Vf is equal to 3AT over 2, the Fermi velocity. So we have then Vf minus, let me use this notation, P1 sigma 2 instead of xy, plus P2 sigma 1. Okay, where these are the Pauli matrices, and then let me introduce these, because Pi is P1, P2, and in 1 plus 3, 1 plus 2 dimensions, so our P mu will be P0, P1 and P2. Now you see, this point I want to emphasize that this is not sigma dot p. It is different from sigma dot p. It is minus p1 sigma 2 plus p2 sigma 1, and therefore the Dirac Hamiltonian, this will be Vf. Now I want to bring it to the form, so I introduce sigma 3 now. So I sigma 3 sigma 1 p1. You know that sigma 3 sigma 1 is equal to I sigma 2, so that it is identical with that one. You have sigma 3 I sigma. And then we will have I sigma 3 sigma 2 p2. Now you see, you have here Vf gamma naught gamma p, okay, where gamma naught I take as sigma 3 and gamma 1 I take I sigma 1 and gamma 2 I take as I sigma 2. Okay, so this is a genuine Dirac Hamiltonian in 1 plus 2 dimension. Remember, our in 1 plus 3 dimensions.
I can always, sigma 1, sigma 2, sigma 3 satisfy a certain algebra.
Yes.
But I can always relabel what they are.
Yes, you can.
So I can call minus sigma 2, sigma 1 and sigma 1, sigma 2. They will still satisfy the same algebra.
Yes, you can do it. In fact, in the other one, we will have something like that one. Okay, so this is actually in the form. Remember, remember, you see this one here. In 3 plus 1 plus 3 dimension, our Dirac Hamiltonian was alpha dot p without the mass term. And since, if you remember, alpha was gamma naught gamma. So this is then gamma naught gamma. Okay, so this is exactly the form which we had here. Now you see the sigma dot p, if for example I have a neutrino, okay, which is massless, if I use a chiral representation, then I showed you last time that in chiral representation this is minus sigma 0 sigma, and then what will be the Dirac equation, for example, in the chiral representation? So this will be acting on psi L, psi R. So you will get either sigma dot p psi L equal to 0 or sigma dot p equal to psi R. So this is actually sigma dot p comes as a 2-component equation in 1 plus 3 dimension. Okay, here the Dirac Hamiltonian is different. Dirac Hamiltonian is this one here. Now, this is the way I have derived it, but if you see, there is another way which I will refer to. There is a recent paper which he actually make a distinction, which is called HD and H Pauli. The H Pauli will be sigma dot p, HD is what I have written here. So there is this subtle difference. In 3 plus 1 dimension for neutrino, for example, massless particles, this will be the Dirac equation. The Hamiltonian is essentially sigma dot p, which is helicity. And the neutrino left-handed means that the neutrino has negative helicity, right-handed means the has positive helicity. So the neutrino is this one, anti-neutrino is this one there. So having said that, let me write also in the covariant form the Dirac equation now. So then actually the Dirac equation will be psi equal to E put here okay, so there will be two solutions, negative and positive energy, and where E will be equal to plus minus Vp, which actually Kashif wrote. Then the Dirac equation will be this one if I introduce this gamma, then this the momentum operator, then psi, I put Vf here. Okay, so let me introduce delta naught as 1 over Vf delta over delta t. In ordinary, this will be the velocity of speed of light, but here it is a Fermi velocity. And then I will have this one, I gamma naught, gamma 1 sigma 1, gamma 2 sigma 2, psi equal to 0, Ri gamma mu delta mu. So this is then the covariant form of the Dirac equation in 1 plus 2 dimensions. The same, there's the same form as 1 plus 3 dimensions. Okay, so if I expand around the second Dirac point K and do the same thing, then this HD will be Vf minus P1 sigma 2 plus minus P2 sigma 1, and which you can write as Vf I sigma 3 P1 sigma 1 minus I sigma 3 sigma 2 P2. Now I took there first time this choice there. In the first I made the choice gamma naught equal to sigma 3, gamma 1 equal to I sigma 1, and gamma 2 is equal to I sigma 2. Now I make the choice here, gamma 1 I sigma 1, gamma 2 is equal to minus I sigma 2, to bring it to the again to the Dirac equation. Now actually these are two inequivalent representations of gamma matrices. Okay, so why it is so? Let me take actually this product of these three gamma matrices. Gamma. Let us take the product of these three here, and let me take its gamma square. And if you use anti-commutation properties, you will find that it is equal to minus. So gamma is then plus minus I. Okay, so this is peculiar to this when you have odd number of dimensions. And because of this, these will be too inequivalent in the means that they cannot be related by a similarity transformation. So we have this thing here for the other one and the other thing. And if I want to write now the Dirac equation in covariant form, I can write it in the form which, okay, so I will do it later, but let me make it here one more point before I proceed. Let me introduce the parity operator now. So let me, this lambda which I introduce in connection with the Lorentz transformation. Now you see in 3 dimension, when you have the parity, all the space coordinates goes to reflective one. But if I do the same here, that is if x1 go to minus x1, x2 go to minus x2, then the determinant of lambda will be positives. So it will not be, it will be rotation then, not reflection. So then I can make this choice. I could have made this choice here also, but that doesn't matter. It is actually totally, you can do that also. But it is convenient in this way because of that minus sign there. Okay, so then it means that P1 will go to P1 and P2 will go to minus P2 and the other ones remain the same. So it means that Dirac Hamiltonian around the point K and that around the point the K prime go to each other, as you can see, because of the negative sign there. So the parity then, so here the determinant lambda equal to minus 1. So it is a reflection. Okay, now I put this Dirac Hamiltonian in a compact form. So I will come back to this operator a little while later. Okay, so let me define here gamma mu now as sigma 3 I sigma 1, then kappa I sigma 2, where kappa is equal to plus 1 or minus 1, depending upon which we have there. Okay, so then the Dirac Hamiltonian I can write as HD V gamma naught gamma dot V with this understanding. Now if I want to introduce a mass term, let me introduce a mass term just for the fun of that, then this will be this will be the mass term here. Now actually I come to this recent paper and that actually tries to interpret what spin means in terms of this. And the reference is this one here. Although it is published in Physical Review Letters, but I give you, because even after publication, they have this version. So you you see, there are many ambiguities in this 3715. It is version 5. Version 5. So it has gone to 5 times the revision. And this is of May 7. And this is after the publication of their paper in physical regulators. So let me go to their interpretation, which you might not like, but let us see how they have interpreted it. As Kasha mentioned, it is usually called pseudo-spin, but they interpret it as the lattice spin. Okay, so let me first remind you that orbital angular momentum is r cross t. And if you have 1 plus 2 dimensions only, you have only the third component. And the Hamiltonian, which I have written there, which you can write as HD in terms of, let me write it in terms of the sigmas. Sigma 3 I, sigma 1 P1 plus I kappa sigma 2 P2 plus. So if you commute this HD L3 and use the properties of sigma matrices, you will find that it is equal to Vf I sigma 2 P2 plus I kappa sigma 1 P. Now if you have HD kappa sigma 3 and do the same thing, you get minus twice I kappa sigma 1 P1 plus sigma 2 P2. So that neither L3 is conserved, neither this is conserved. And therefore you have HD L3 plus I by 1 over 2 kappa sigma 3 equal to 0. Okay, so let me go back to this Hamiltonian, which we wrote as. So since I have introduced a mass term, I will have this 1t, and then I have I over 2 as P dot A1 plus A2 minus 3 under root over 2 kappa P dot A1 minus A2. Okay, so here we have I over 2. So I have I over 2, then P dot there I have minus I by 2, and so I have plus I by 2 A1 plus A2 minus 3 under root over 2 kappa P dot A1 minus A2 and minus MF No, I should have here something like that. Okay, let me now introduce this one with these people as minus AS minus 3A over 2. This is the unit vector, and A1 minus A2 over 2 AD, the unit vector here. So this is 3 under root over 2 A. This is a unit vector. And let me introduce the third one, which is AD cross AS. Then you see this HD can be put as VF K sigma 1 P dot AD, a unit vector AD, plus sigma 2 P dot unit vector AS plus MF sigma 3. Okay, so then it can be put here. Now then they define actually, so they define this spin vector here as H cut over 2 kappa sigma 1 AD plus sigma 2 AS unit vector AS plus kappa sigma 3 unit vector AN. So they define the spin vector by this one here. Okay, so instead of having the usual coordinates x, y, z, they actually take the lattice vectors, in a way the combination of this. If you see their paper, they have the picture here, which Kashif also drew, where these direction are, because A1 and A2 is like this one. So you have to either add this way or add this way. And that is the two directions which they have there. So then you see, you can easily check that if you have Si, Sj, so they satisfy the usual commutation, the basic requirement of the spin. Okay, so then they say that this HD can be written as 2s VF over H, then S dot this vector U, and where U is P dot AD plus P dot AS plus this kappa times M VFAN. So this is the vector. Okay, so they put it in this way where S is defined, the spin, and they call it lattice spin because it is, expansion is with respect to the vectors which are related with the lattice vectors here. And then you can easily check also that neither HD equal to 0 the L is defined in the usual way. HD S is not equal to 0, but H d L plus S dot an. So they call it lattice spin to distinguish it from the electron spin, which you will expand in terms of x, y, z, etc. Okay, so this is this latest paper which you have. You see the similarity actually. If you see the Dirac Hamiltonian in 3+1 dimension, you have alpha dot p, and you can write it actually as gamma phi sigma dot p, where this capital sigma is the diagonal matrix which I introduced there. So you see the similarity here. Instead of this sigma you have S, instead of vector p here you have vector u. Okay, so this is the what I mean. So I have gone through the derivation of the Dirac equation. I say the genuine Dirac Hamiltonian comes in, but if you select your these actually the lattice vector which I have defined. Now these paper, actually this paper also he write HD, which I have written. Then they write HP also, which will be like sigma dot p. But then they make a choice with the different types of, they draw the figures if you see there, with the different types of expansion is not the A1, which I have A2, but the coordinate axes are actually rotated in a way there, and then you get this. So they make a distinction between the Pauli type here and the Dirac type, which we have derived. Because Dirac type must have this type, as we have seen in 1+2 and 1+3 dimension.
So later if I want to rotate this, the two-component spinner around the z-axis,
yes,
then I use the usual L plus S as the generator of that.
Yes, yes. So they actually write if you, because you have this the rotation, the well-known rotation that in the spin you have I S dot actually theta by 2. So, and they consider this also in this paper. This type of rotation is there also. So it is in a rotation, but with respect to the axis which they have introduced actually. So maybe it is an interesting observation. Whether it has deep meaning, I don't know. What do you think?
I have to think more about this.
So there is a magnetic moment associated with this lattice spin as well.
Yes, yes.
So what's the G value for it?
I don't know. One can work out there, but I don't know what will be the G value.
Completely analogously, one can.
Yes, yes. But I will introduce actually also in this context when we have an external electromagnetic field, and then we will have that type of term which we have in the 3+1 dimension, that is this sigma dot B. Okay, similar type we will have there also, but it will be quite a different type of thing actually. So whether it can be, so in my second lecture or maybe I will do that, but let me continue with the parity operator here.
If you want to include the effect of an external magnetic in Zeeman term, you have to put that by hand. It's not going to come out of this.
Yes, the magnetic moment doesn't come up, but an abnormal type of current actually comes out of that, which I will show. Okay, so let me just do a little bit about the parity operator. Okay, so the parity, so our xp will be the coordinates and t x1 minus x2. Now let me introduce here this notation delta gamma naught delta naught gamma 1 delta 1 plus gamma 2 delta 2. And let me introduce this one also, gamma 1 delta 1 minus gamma 2 for the two representations which I did. So in the first representation I will have this as I wrote down the covariant form. So let me introduce actually the mass term here because it is instructive to consider this. So this will be when I expand along the Dirac point k prime, and then I will have second will be I del minus m dl psi minus when I expand with respect to the second Dirac point. So I have these two equations 1 and 2. So let me write these equations in terms of the reflected coordinates. So if I do that, I will have I gamma naught delta naught p, which is not affected, plus I gamma 1 delta 1p. Then I will have this minus sign delta 2p psi plus x equal to 0. So this will be the first one here. And the second one then becomes I gamma naught delta naught p I gamma 1 delta 1p plus I gamma 2 delta 2p psi. So let me call this equation 3 and 4. Now the invariance then requires, so I can write these equations if we take psi plus pxp equal to minus some phase vector psi minus x, and if I take psi minus p xp equal to minus p minus eta p psi plus x. Okay, then the invariance is ensured provided I have this one here. If I have this one here, then what will be the first equation? So then it will become I, so this I delta p, the first equation, minus m psi minus p xp, and then I will have this one bf psi plus p xp equal to 0. So then these equations will be invariant, but we have to take them together. Actually, under t, this goes to this to psi minus, and this goes to psi plus.
So minus sign is just convention, right?
This
You can absorb it in the phase.
with this minus.
The minus sign in front.
Oh yes. This is just arbitrary. I mean, this can be absorbed in eta p. So actually, so this is so in the 3 plus 1 we could find this matrix here, which actually, as you remember, then psi p xp. was equal to gamma naught psi x. So this was there. But here we have to do actually we have to take care of that. Now for our later work, it will be convenient if I actually make this redefinition.
It's the same thing as psi, because in the four-dimensional psi left went to psi right and psi right to psi
Yes, similar type of thing. Yes, it is similar type of thing. So one goes to the other. Yes, there also psi L goes to psi R, psi L. It is similar type of thing. So let me redefine the fields. Redefine these. So let me put psi A equal to psi plus, and let me introduce psi B. Why I want to do it? Because I want to, it is convenient to write everything in terms of this delta, not using delta and delta tilde. So let me therefore define this I gamma to psi minus. And then we can write our two equations as I del minus m vf psi a x equal to 0 and I del plus m, this is important, psi b x. So that is why I introduced the m here. So plus m comes here, and here minus m comes here. Okay, so then delta is simply the usual one which we have in the Dirac equation, gamma mu delta. Okay, so this we have here. So in terms of these, let me also give you the parity transformation for this one here. So this will be similar to actually what we have for neutrinos. So psi a pxp is equal to, as we have seen, psi plus pxp, and this will be equal to then minus I eta p gamma 2 times psi beta psi bx, or it will be eta p. That is why I made this choice of minus there. So it will be then eta p sigma 2 psi bx. And if you remember, the neutrinos also have these transformation properties. Psi b p xp will be then eta p sigma 2 psi a. So you see here the parity interchange is psi a and psi b, which is not the case for the 3 plus 1 dimensions. You have one there. Okay, so let me now just introduce, if we have in the these quasi-fermions in the external gauge field. And we will continue in the next lecture, but let me just introduce it here. Okay, so after I have introduced, let me introduce the gauge field in the same way as we did for that one, which which is electromagnetic. Mu. Then this delta mu goes to d mu plus I e c a mu. Let me keep c here. Okay, so then you will have I d mu psi a or psi b, whatever you want to use. It holds both of them. Okay, so I do exactly the same thing as I do for the other. So we multiply in the 3 plus 1 by minus I gamma nu d mu. And then we get here is gamma mu d mu psi a equal to 0. Now, just as we did there, we have sigma mu equal to 1 over twice psi and g mu is this thing gamma mu plus gamma mu. So as we did there, so you can easily check that d mu as there is I e over c f mu. And then our equation is d mu e over 2c f mu nu psi a equal to 0. So again you have this additional term here. Okay, what is this additional term here? Now in this gamma matrices here we have only gamma naught, gamma 1 and gamma 2. You can easily check that sigma mu nu in this particular case will be epsilon lambda mu gamma. So this is the difference here. And this you can easily check that this is satisfied here. Okay, I don't have to write here, so we have then E over 2c sigma mu nu f mu nu is equal to E over 2c epsilon lambda mu nu f mu nu gamma lambda, and this you can write fj lambda times gamma lambda, where j lambda is E over c epsilon lambda mu nu f mu. Okay, so the induced current is then J lambda. Let me do this and then we will finish it. Okay, so the induced current is J lambda E over C epsilon lambda mu f mu. So I will put here, because I take this, put here. Okay, so what will be the induced charge then? Induced charge will be d cube x j naught xt, and this will be then E over c f epsilon ij, because we have here two dimension only, epsilon ij fij, and this will be E over c epsilon ij delta I aj minus delta j I, or it is equal to twice E over c this one, the third component, or twice E over c times the magnetic field. So this is actually J naught is equal to this one. So the charge induced is then so the induced charge is then Q equal to twice over C d square x, because it is two dimension, times B, so it is twice E over C times the magnetic flux. Okay, so in the static background which we have, A naught equal to 0 and AI dot is also equal to 0. So we have this one here. So for the quantized flux, we have N. Now there is interpretation of these which I do not very well understand, but let me, in any way, this is actually in the seminal paper by Seminov. The way I have done is was done by Jacques. So he did it in a different way. So Seminov this is PRL 53 2449. Okay. So I am taking a little bit of your time because you will not be in the second lecture, so I want to do it in your presence.
This is the conserved current J lambda. So this corresponds to the transformation psi goes to the I alpha psi, the usual gauge transformation.
Yes, yes. So this we have. So this actually can be, better can be actually interpreted as topological charges. Now here is this thing that I gave you that in the Dirac whole theory. So we have these ones here, and there we have M, this constant, and we have this one here, minus M. So these were E greater than 0. So this is empty in vacuum, and these were filled in vacuum. And this gives a gap between the two. Now if M is 0, what where is this mid gap? Okay, it is with E greater than 0 states, or it is with E minus 0. So this ambiguity is there. So if there are, so if for zero energy, these charges actually are minus, so if they are quantized, so in unit steps, then minus twice E phi plus E and plus minus E twice E phi and finally twice E phi. So what is the gap between the two? The gap is twice E phi. Okay, so this thing be good. So if phi is n, then Semenoff there we have 4n plus 1 degeneracy here. Okay, because you see, if you just it is arithmetic progression with d equal to the difference E. If you start from minus E to phi and end with 2E phi, then the number of n prime minus 1 will be equal to 2E phi, so that n will be equal to 2E phi plus 1. And since you have n, so he says you have 4n plus 1 degeneracy for the ground state. And this is his conclusion then. And then I will, in the second lecture, I will see this current which I have introduced, this abnormal current, and this will be coupled to actually a current which will be see there. And Semenoff then says that it is because it has abnormal parity, this current, so it is in a way is unphysical current. And then he says how one can see the effect of such a thing in terms of the Zeeman type of thing, which I do not understand, because he considers the pair is then have zero mass, and then he says maybe there is a Zeeman type of splitting and this effect can be seen. But since I don't know anything about condensed matter, so I cannot say anything. But this is an interesting observation he has made, because when you have massless particle, then where to put the mid gap? And this ambiguity is there, and this lead to the degeneracy of the ground state. And it is 4n plus 1 fold, he says, the degeneracy. And factor of 2 you can understand, because you have this up and down. So the factor of 2 you can understand. But you have, so there will be 2n states, because one up, one down. That you can understand. So I finish there, then we will continue with this. So but I wanted to do it in your presence.